while everyone is joining, maybe we can introduce a little bit ourselves. Today, you'll be joined by myself, the Head of Business Development here in Newtwen. And I'll briefly introduce the topic and set the stage for today's discussion. Then I'll hand over the conversation, the presentation to Francesco, our founder, CEO, and technical lead, who is the person for sure behind much of the technology we'll be discussing today, and certainly the best person to guide us through the technical aspects of virtual junction temperature estimation. So, power electronics have become one of the key differentiators in modern electrification. Whether we are talking about electric vehicles, industrial drives, every industry is pursuing the same objectives: higher efficiency, higher power density, faster time to market, and obviously lower costs. What's interesting is that while the semiconductor technology has evolved tremendously over the last decade, the way we protect and operate those devices has changed surprisingly little. And that's exactly what we will be discussing in today's webinar. Now, we are seeing that every engineering team is facing the same challenge. On one side, you want to extract the maximum current available and push the performances of your hardware to the limit that can safely deliver. But on the other hand, you need the complete confidence that eventually you will never exceed the thermal limits of your power devices. The problem that we are also seeing is that junction temperature remain one of the most critical variables in the entire system. Yet it's also one of the few variables that we simply cannot measure directly in production. So, what are we doing? We are controlling the device around the worst case assumption. The consequence is that the systems around the world are operating well below the actual capability, not because the hardware is not good enough, but because the controller doesn't truly know what's happening inside the silicon. So, when the controller doesn't know, it has only one option, which is staying conservative. We are seeing that companies are staying conservative in controlling the temperature in their devices with more derating, larger control systems, higher safety margins, and therefore less performances. At Newtwen, we believe that the future of these devices looks different. Hardware has reached an incredible level of maturity, so the next leap in performance won't come from building stronger hardware alone. It will come from making hardware smarter. Imagine a controller that knows in real time the actual junction temperature of every power semiconductor. A controller that can continuously balance performance, efficiency, and reliability based on what's really happening inside the device instead of relying on assumption. This is more than temperature estimation. It's about giving embedded systems full visibility into variables that have always been hidden. It's about making power electronics increasingly self-aware. In fact, temperature is simply the first, but probably the most valuable step in that journey. Now, during today's webinar, Francesco will explain how this is made possible. We'll walk you through the challenges behind accurate junction temperature estimation, the limitation of conventional approaches, and how physics-based reduced order models can deliver highly accurate real-time junction temperature directly inside your embedded controller. And with that, Francesco, I will pass the word to you.
Thank you, Andrea, for the kind introduction. So let's start. I will share my screen with a presentation. Can you confirm that you can see the presentation in full screen?
I do, yes.
Great. So, nice. Today I would like to talk you the main challenges and problems in designing and control power electronics in general that, as Andres already mentioned multiple times, they are tied to the junction temperature estimation and control. So what we have seen so far in the industry, there is a huge problem around that. So people it's evaluating and buying different power module, trying to reduce the silicon die area, but also at the same time trying to satisfy some, let's say, current requirements for the product itself. So it's not an easy task, and in this process usually relies on trial errors, building different, let's say, prototypes, pushing with the limits, but still, let's say, companies are using safety margins that are tied to the confidence that they have in the production readiness of the product in the junction temperature, so in the thermal limit of the let's say device itself. So our technology actually wants to act like an IR camera, so a software model that represent the junction temperature hotspot inside power electronics devices, which act like an IR camera that is running in a microcontroller unit, and it's giving you, let's say, direct access to the hotspot of the power electronics itself, and we will see in a moment all the challenges related on that. And providing this information, you can basically reduce the thermal room and the safety margin, so pushing with the performance and the safety of the device itself. So the main goal and objective here is to estimate the hotspot of power electronics. To do that, we have created our software methodology and our software platform, which is called Twin Fabrica, and that I'm also giving you taste today of how it works. However, let's firstly focus on, let's say, the technical challenges around power module junction temperature estimation, which, as already been mentioned, is one of the most critical variables to be controlled and to be monitored inside power electronics devices. So, first of all, when you have a real-time model in production, what you have to do is to calibrate. So having just a physical model, it's not enough because of manufacturing tolerances, aging conditions, unknown boundary conditions most of the time. So if we really want to reduce the thermal room, a good experimental campaign with a ground truth validation of the junction temperature must be conducted. To do that, of course, there are, let's say, several methods. And the first challenge is the measurement of the junction temperature. In the case of power module, like this example here is on an Infineon FS03M MR12. It's a next generation of power module, silicon carbide based. It's a traction inverter. To measure the junction temperature, working with the supplier, working with the customer, or working by consulting. I don't know how the customer will, let's say, collect this data, but there are, let's say, standard methodology to measure the junction temperature, and it's quite relevant. So in this case, the module was open, as you can see from the picture here. The insulation gel was removed, and by means of IR camera, the entire chipset dies has been recorded with, let's say, a standard procedure. And for the moment, I would like to focus on the standard procedure because it's quite relevant. So I will skip in a moment to this slide to show you which is the standard procedure for this kind of power module. For different technology of power module, there are different procedures, of course, to measure the junction temperature. Basically, here, as you can see, on the right, you have the IR camera, and on the left, you have the real-time thermal model that is acting like an IR camera, as I mentioned before. So using IR camera, you have the chance to place, as you can see in the image, tiny, let's say, elliptical surfaces centered in the die of the corresponding chip. So, for instance, let's say that the switch of phase U low, in this case, is composed by 6 dies, so we have 6 elliptic areas from E1 to E6, as you can see from the image on the right. And the junction temperature, it's the average of the pixels recorded by the IR camera at high frequency rate, of course, if we want to see the full dynamics of the temperature, as we will see in a moment. And this will be the so-called virtual junction temperature recorded and used as ground truth data for the calibration of our physics-based real-time model. It's very important that we take this in mind, because this is usually the standard procedure of suppliers when they are writing in the data sheets of the component itself, junction temperature. This is the kind of, let's say, normative that they follow in order to measure the junction temperature. So, for instance, if you want to try to collect the right data set in order to validate and calibrate your model, don't take the maximum pixel, because you are, of course, including already a huge thermal room. In fact, if we see the difference between the hotspot, that is the maximum pixel in this IR camera, and the average in a single switch composed by the parallel of 6 dies, you already have a thermal room of 15 Celsius degree. Sometimes it depends, of course, by the operating point. However, 15 Celsius degree, it's a lot of current that you are leaving on the table. So, given that, it's important to have a standard procedure for collecting data on the junction temperature in order to have ground truth. Of course, in production, when your inverter it is fully, let's say, built, you don't have this kind of setup, right? So you can only rely on current measurement, voltages, polydiodes or NTCs, whatever is the thermal sensor technology used by the supplier of the power module. So your model now can just rely on this input data and has to estimate the maximum junction temperature in the system. And has to estimate this in a microcontroller unit that, for instance, has limited memory and limited computational effort. So, as you can see from this, let's say, schematic image, inside the microcontroller, the input of the model will be the phase currents, output of the inverter, the DC bus voltage, that will be, of course, measured, the switching frequency imposed by the controller, the duty cycles, and the integrated thermal sensors, NTCs or polydiodes, whatever it is the technology used. The output of, let's say, the model will be the estimation of 6 temperature switches in the junction and the real-time calculation of the maximum among these 6 switches, which is not always said that is, let's say, the same switch. It can change and it can vary by different operating condition and different cooling condition. The second output that you can see here, it is instead a closed loop control. So basically, if you have the chance to estimate in real time with high accuracy, so reducing the thermal room, reducing the safety margin, the maximum junction temperature in your system, you also have the chance to control it. And you can do it with, let's say, a simple control library that we deliver with our software technology together with the digital twin that you will create of your power module of your inverter. So now let's see which are the technical challenges that the model has to tackle in order to estimate with a high accuracy. So acting like an IR camera, so an accuracy of, let's say, plus minus 5 Celsius degree in all the conditions. So just to recap which are the conditions, here we can change operating points, so current, switching frequency, DC bus voltage, but also the module itself can change. So for instance, between module 1 and module B, even if they are of the same, let's say, supplier and family, you have manufacturing tolerances. Sometimes you have also variation of RDS on of 20% respect to the datasheet, right? And that 20% of variation is reflected in a 20% or even more variation in the power loss. And so different temperature and thermal behavior, right? So even there, usually customer, what they do, they know that the RDS on can change, and they take another thermal room, so other safety margin on the estimation, once again leaving on the table a lot of current. So one of the technical challenges will be to be agnostic to manufacturing tolerances in this case. And also this can be, let's say, tackled by our software technology. We will see in a moment how. And the third challenge that we have to solve, it is time-varying boundary condition. If I go back here 1 second, as you can see, in the microcontroller unit, most of the time I don't have any guess about the coolant flow and the coolant temperature. But the coolant flow and the coolant temperature of my inverter, they change a lot the thermal dynamic of the junction temperature we will see in a moment, no? So the model has to predict this time-varying boundary condition and to correct the estimation, so to adapt the accuracy estimation in order to achieve the 5 Celsius degree of error in all the condition, even if we have time-varying boundary condition. And this will be the third challenge that we are going to solve. And then we have the latest. The latest challenge that we are going to solve, it is on faulty conditions. So we have also extreme condition that we would like to, let's say, address so that our model has to predict with high accuracy. And I'm talking about, for instance, coolant fault. So when, for example, in your inverter, you have the pump of the cooling system that is on fault, so the coolant flow is not flowing anymore in the inverter, so the speed of the coolant is 0, and you have a complete different behavior in respect when the coolant flow is at the nominal, let's say, flow rate, or even in the worst case condition, when you have the dry operating condition. So for instance, a loss in the pipe of the coolant, and now the cooler of the inverter is completely empty, you have air inside, and once again the thermal behavior will be completely different with respect to the nominal condition. So these are the 4 challenges that now we are going to tackle. And let's see how the model behaves. So for instance, it's important that during the, let's say, commissioning test campaign, using, for example, the IR camera, so with a setup of this kind, it's important that we operate the inverter in different conditions, changing also the coolant flow, the boundary condition, so the coolant temperature, and also the power module itself can be changed, so that we collect few tests data, let's say, usually 4, 5 full test bench campaign. It's enough to collect this kind of data in order to calibrate the model and to achieve the target accuracy. So from the following slides, what you will see, it is the experimental results during the validation. So the model has already been calibrated and integrated in the microcontroller unit. After this, I will show you how we can calibrate a model and we can implement it in the microcontroller unit, and how easy it is with using our software. And on the left, you will see the current emission profile, in particular the RMS profile of the current during this 1 minute of operation. In the top, you can see the coolant and the switching frequency and the DC bus voltage condition. So for example, in this test, we had 35 Celsius degree of coolant temperature, 5 liter per minute of coolant flow rate, 20 kilohertz of switching frequency, and 900 volt of DC bus. And on the right, you can see the step response, basically, of the temperature with the current. We have 6 colors from dark blue to light blue, basically, as you can see here. monitoring with the IR camera the junction temperature in all the switches, the switches, using the, let's say, measurement setup that we have shown in the previous slides. With the same color but dashed line, you have the virtual thermal sensor estimation, so the real-time thermal model implemented in the microcontroller unit response. So the last step, it is highlighted because in the next slide, I'm going to show you the error. The error calculated at each single time stamp. So IR camera recording minus microcontroller estimation recording by CAN. And you have for each single switch the error between the IR camera measurement and the model estimation in real time. As you can see, there are also two boundaries of plus minus 5 Celsius degree that they represents the target accuracy and tolerance that we want to achieve. Now it's time to change. It's time to change condition. So here we have tested with 20 kilohertz and specifically a certain current emission profile. But now if we change the switching frequency and the cooling also, in this case 8 liters per minute, not more 5, we have also changed the DC bus voltage, but specifically here we have a test with the 8 kilohertz. What we can see is that still the error is within the accuracy tolerance. Because if we have a look at the last time step response of the temperature, the error during that, let's say, transient, it is within the tolerance. Now, if we use the same identical condition, so 35 Celsius degree, 8 liters per minute, 700 volt, and the same identical current profile, but we change the switching frequency from 8 kilohertz to 20 kilohertz, in this case, of course, the temperature is much higher, and still the error is within the tolerance. Now, the other, let's say, electrical parameter that we have to change, because in the inverter itself can change, it is the DC bus voltage. So for instance, in this test, we have 550 volt and a certain, let's say, thermal step response of the junction temperature with the error within the tolerance. And if we change completely the DC bus voltage between 550 and to 900 volt, of course we have a higher temperature with the same current because the switching losses has raised because of the, let's say, higher voltage of switching. And so the error is still very good. So now, until this moment, we have just taken and demonstrated that with these real-time models and the methodology that we have built and automatized in a Unix software platform to create your digital twin, it's quite easy to basically obtain a very high accuracy, changing electrical parameters, changing electrical condition like current, switching frequency, and DC bus voltage. Let's say that until here, it's not so difficult to let's say, achieve this because you can calibrate both current voltage and switching frequency. They are known in the microcontroller unit, so they are time-varying input that you can use. And now let's start with the second phase, that is one of the most challenges. So changing the boundary condition, and specifically the coolant flow. So now we are going to demonstrate that even if we change the coolant flow from 5 liters per minute to, let's say, 12 liters per minute, which is the nominal condition, but holding the same identical, let's say, voltage, switching frequency, coolant temperature, and current emission profile, like in this case, the accuracy is still quite good. What does it mean? It means, so here you can see that we are within the tolerance with 5 liters per minute. And here, if we change to 12, of course, also the profile of the current, the dynamic of the profile of the temperature, so the dynamic of the temperature has changed because, of course, the coolant flow has changed. And what you can observe is that the model is capable of predicting this time-varying boundary condition and to adjust the thermal dynamic of the current thanks to, let's say, an inference model that is using the polydiodes inside the power module itself. So by the thermal response of the implemented sensor in the power module, the model is capable to understand that is a time-varying boundary condition and to correct, by consequence, the junction temperature estimation and dynamics, holding a very good accuracy, 5 Celsius degree, an accuracy that is, let's say, coherent with the measurement tolerance of an IR camera. So, coolant flow for sure was one of the challenges, but also the coolant temperature can change, because if we think about the chiller in a cooling system, not always it operates with the nominal, let's say, temperature of the coolant. And sometimes, not in all the system that we operate within, the coolant temperature is a known variable. So sometimes you don't have information on the temperature of the inlet of the coolant. And unfortunately, this temperature variation has not a linear behavior, in the sense that if we change now from 25 Celsius degree to 70 Celsius degree, the difference in the final temperature junction is not 45. It is more, and it is more because the system is non-linear. So if we change the coolant temperature, the junction temperature change, and the power losses, they change. So your model has to take into account also about this. But most importantly, your model has to understand that you have a coolant temperature variation, even if it is not measured. That was the challenge. And as you can see, our model is capable of taking it. So if we have always the look of the final transient behavior in order to basically check if the tolerance is always satisfied also with this 25 Celsius degree condition, and then we change temperature cooling from 25 to 70, and we have a look, as you can see, we have much more than 45 Celsius degree of variation. In this case, we have almost close to 65, okay, respect to the previous operating point. As you can see here, the maximum junction temperature is close to 145, like instead before it was with the same identical current, but changing the coolant flow, it was close to 85. So absolutely it's not the delta 45 Celsius degree. And this is a common error. We have seen many times with our customer that they basically normalize the coolant temperature, let's say, operating point, and then they scale it with the first reading of the NTC. Absolutely, it's not the right case, because the model is not linear. Now, as I mentioned before, the third challenge was on the manufacturing tolerances. So let's think about two different phenomena. One is manufacturing tolerance, in the sense that module by module, even if in the paper they are identical, in the reality they are not, because of, let's say, all the processes when you are manufacturing it, all the, let's say, impurities, different pressures, etc., etc. So could be that from the data sheet you have a certain RDS on, the nominal value, but actually there is a variance around that, and this variance can also be 20%. So you can have in some module, in some, let's say, unlucky inverters, power modules with the RDS on 20% higher. And in fact, what does it mean? It means that with the same current, you achieve higher temperature with that. So here, customers usually what they do, they take, once again, thermal margins, because they say, my model cannot predict this, let's say, manufacturing tolerance variation, and for this reason I have to take another thermal room of 20 Celsius degree. So if we compound all these thermal room, 20 Celsius degree because of the manufacturing tolerances, 15 Celsius degree because of the IR camera measurement or the ground truth measurement, that I'm taking the maximum pixel instead of the average. If we take other 10 or 15 Celsius degree because the boundary conditions are unknown and I have to basically calibrate my model against the worst case. thermal room by thermal room compounded, we are leaving on the table a lot of current. And a lot of current, it means that with the same current requirements, you are improving the silicon, you are increasing the silicon die area, and so the cost of your final inverter. So having a model that it's capable of predicting also in real time this kind of phenomena, so have a right estimation of the junction temperature independently by the manufacturing tolerances, really helps during the design phase and the control to push with the current and so to minimize the design hardware. In this case, what we have demonstrated is that, of course, our model doesn't have the RDS on, let's say, real-time measurement in the microcontroller, but it's capable, thanks to the, let's say, test plan commissioning that I was mentioning before, to predict the junction temperature even if the RDS on is changing of 20%. So let's say we are manufacturing tolerance agnostic. And we will see in a moment later how it is possible that. Just changing slide, here you have the, let's say, dynamic error of the previous slide. So always higher camera minus junction temperature for two different power modules in the same inverter kit platform, let's say. And then there is the last challenge. The last challenge that I mentioned before was faulty conditions. And in particular, we have, in this case, analyzed two different faulty conditions. One, it is on the, let's say, electric pump of the coolant, that now it is on fault. And so the coolant, it's with 0 speed. You have 0 liter per minute, but you have still water glycol inside the cooler of your inverter. As you can see, we have almost 200 amp and let's say dynamic that is completely different from before. Why? Because you have a huge, let's say, mass of water glycol inside the cooler with a huge heat capacity, let's say, and you have to predict this behavior. So in this case, the model, even if doesn't have any kind of information, even if has not been calibrated with this condition, but now the model has learned the physics for different boundary condition, and from the NTC behavior or the polydiode's behavior, it's capable of correcting the junction temperature. The error within this full, let's say, transient of faulty condition is still between the tolerance of 5 Celsius degree. And this is a very good opportunity for us, because it allows to basically improve drastically the safety of the inverter. In fact, now we can see the last and also the most dangerous condition, the dry cooling condition. So in this case, the fault is not more in the pump, but it is in the pipe. So basically, you have some loss, and inside the inverter, you don't have any more water glycol. So let's say that the inverter is completely healthy. It's not broken. It's not on fault. It's the cooling system that is on fault. Now, if you don't have coolant inside the cooler, the dynamic is quite fast, because you have air. You don't have anymore the let's say the water mass capacity, and the classical, let's say, functional safety procedure, they are not fast enough to basically recover and to, let's say, improve the safety of the inverter during cooling system faults in this case. Imagine this. We all know, and we will see in a moment, that NTC behavior, that is the sensor, let's say, placed far actually from the junction in the power modules usually, it is quite slow with respect to the junction temperature, right? So imagine that in this case, with this, let's say, dry cooling condition, the time that the classical functional safety procedure, that is, if NTC temperature is higher than 95, 100, whatever it is your limit for functional safety, then shut down the current, the time that it takes for the, let's say, NTC to achieve that temperature, the junction temperature is already fried with dry cooling condition. So in this case, it is better to anticipate. And to anticipate, it's possible only if you have the junction temperature estimation in real time. So in this case, you can see the control architecture also in place using a closed loop with the junction temperature, which is derating the current to, let's say, a dynamic limit such that the junction temperature, it is, let's say, safety driven within the tolerance of, in this case, 90 Celsius degree. So how the controller behaves? The controller in the first seconds understands that the dynamic is quite, let's say, different from the operating condition cooling. So in this case, the controller set a new temperature limit from 175, that was before, to 90 Celsius degree, like in this case. So there is a new temperature safety limit set. And then once the junction temperature achieves that limit, there is the derating current condition that you can see on the left, that is, let's say, lowering the current such that you control constant the maximum junction temperature in the system. This has two main advantages. The first, it is the safety. My inverter is completely healthy, and what I have, let's say, on fault is the cooling system. So I don't want to break my inverter because I have a fault in the cooling. And with this control, is something that I can achieve. Something that with the standard classical functional safety procedure, you usually compromise the inverter. So you are forced to oversize the inverter also to, let's say, take this kind of, let's say, faulty conditions. Instead, with the second, there is another point that can give you a competitive advantage, which is the service of continuity. So in this case, my, let's say, functional control, it's capable of derating dynamically the current such that you control the maximum available temperature during a faulty scenario. What does it mean? It means that the final current is not zero. The final current is the maximum one that you can tolerate during faulty condition. And this, for instance, of course, you don't have the same nominal condition, but at least you can preserve the continuity of the service, even if on a, let's say, lower operating point. And that is quite, let's say, useful, for instance, to recover by default and to allow you in the automotive application, for example, to arrive to the first, let's say, recovery station and to fix the fault. Now, there is the, let's say, and here you can also see the kind of error dynamics during that fault condition. So we are always within the higher camera tolerance. Now, the last thing that I want to show you before we deep dive with the software platform and we can see step by step in a quick, let's say, demo how to achieve this kind of results and how easy it is. The execution time and the memory footprint. So, okay, very nice model, but does it really run in real time in the micro, or do I need, let's say, very expensive microcontrollers? Absolutely not. So this model is super accurate, but it is also quite, let's say, light in terms of computational effort. So for instance, these numbers on execution time below 50 microseconds and memory footprint below 25 kilobyte of the model have been achieved using a standard automotive platform, in this case Infineon Aurix TC387, and the model has been implemented in the derating task of 1 millisecond. So let's say the slower task, not to the PWM, we don't need to go fast as the PWM, since thermodynamics, they are not fast like the electrical one, but 1 millisecond, it's, let's say, good enough to see huge temperature variation, so fast dynamics of temperature. So, finally, if, let's say, we want to summarize what does it mean have in the microcontroller unit a good and reliable real-time model of the hotspot, so the junction temperature, it means that you can increase the maximum available current in all the operating points. You can, let's say, better manage the power during all the conditions, also during fault. You can lower the thermal, let's say, headroom, so the thermal room, so the safety margin basically. And if you use these also during, let's say, a design phase, potentially you can buy a power module that is, let's say, with less silicon die area inside, so a cheaper one for the same identical current target. And this, of course, is the kind of competitive advantage that allows you to not only have, let's say, an optimized hardware, but also, as Andrea has mentioned at the very beginning, to differentiate with your competitor, because now your inverter becomes smart. Now your inverter can selfly manage the temperature at the maximum limit in all the operating condition. So implementing digital twins in real time inside product, it means that you have much more real-time information, and that the information can be processed with thermal, let's say, control library, and that is exactly the definition of intelligence. So taking decision about, let's say, processing information. More information we have, better or smarter decision we can take in the control of our power electronics. So now I want to deep dive into the software platform that makes all these kind of, let's say, methodology and procedure easy, let's say, because customers actually, they are already doing this. They manually design thermal networks, let's say equivalent electric circuits. They try to do some experiments, they collect data, they calibrate. It's a very long process, right? And most of the time they spent many effort, time, resources in calibrating a power module. And then there is a new inverter coming with a new power module, and the old, let's say, thermal model doesn't behave, of course, rightly with the new hardware. And so you have to repeat the process, and this process is long, it's manually done. There is not, let's say, a single software platform that can manage all the steps necessary to create this final firmware implemented in the microcontroller. And that is exactly where we are positioning ourselves and our software offering. So in this case, in few steps, what you can do within Twin Fabrica, you can import the 3D geometry and you can simulate. So basically there is a finite element solver inside Twin Fabrica that can already give you an idea of the behavior of the power module even during the design phase. So you can change current, boundary condition, coolant flow, voltage, switching frequency, whatever. Once you have a, let's say, good understanding of this, let's say, power module behavior, what you can do, you can reduce it. So, for instance, this model here, which is basically a FEM, we can see there is a mesh, etc., etc. It has almost 1 million of degrees of freedom coinciding with the node of the mesh of this power module. So good model, but it's unpractical to be implemented in the let's say microcontroller unit, right? So the second step of our software, it is the model order reduction. Model order reduction recently has been also developed by some commercial tools. However, the model order reduction library that you can find in Twin Fabrica is the unique one that can handle nonlinear problems. And as we mentioned before, these, let's say, models, they are nonlinear. So you have to achieve a model, in this case, of just 40 nonlinear equation that is capable of representing with high fidelity the physical behavior of a full FEM. It is a methodology that is quite different from the, let's say, classical thermal network modeling, because model order reduction preserves completely the accuracy and the resolution of the geometry. Let's see. So simply no code, you just build the ROM and the software generates the reduced order model that then you can analyze. So now I will basically, let's say, show you if I compute now the solution using the full FEM of 1 million, and then I compare the solution of the 40 equation nonlinear reduced order model, and I reproject back, let's say, the solution in the full mesh, so I don't lose the mesh information. As you can see, the error it's close to zero. So I have obtained a reduced order model that is basically behaving in dynamics, in steady state, in frequency domain, like a full FEM. This is much different from a thermal network because I preserve the full geometry, and it's relevant for the next phase, since the next phase is the calibration. As I mentioned before, it is relevant to collect data on test bench, right? Because in the microcontroller unit, unfortunately, there are a lot of conditions unknown, like the coolant flow, the coolant temperature, and also in the real, let's say, product and device, there are a lot of, let's say, phenomena that you cannot model with the physics, like aging, like manufacturing tolerances, etc., etc. So it's something that you have to calibrate using data-driven methodology, so edge AI in this case. So the first thing that you have to do is to have a very good representation of where you're measuring and where you're estimating. And that is quite simple in TwinFabric. I just click the node of the mesh, basically, in the domain where I'm measuring with the IR camera. And in this way, I will nominate the virtual sensor like the one that I'm collecting in the IR camera. That is the first step. And this is a very, very important step because it helps me to calibrate point by point the physical behavior respect to the real experimental setup. The second one, it is the import of the measurements. So within TwinFabric now I can, in this case we have more than 100 different tests, also testing different power module for this FS03. Let's have a look on one of them. You can import the recorded data, for instance, switching frequency, it's an electrical parameter, the RMS current, as the one that I shown before, DC bus voltage, 900 volt in this case, and also I can see the behavior of the polydiodes in the power module together with the IR camera measurements. So as you can see, here you have a good variation in respect to the hotspot. So what we are reading in the polydiodes and what is the hotspot in the junction, of course. But now I have all these tests that I can use to refine my reduced order model such that from these two polydiodes reading, it's capable of correcting the junction temperature respect to a lot of conditions. So the test campaign that I was mentioned before is quite relevant. We need to minimize the number of tests such that we obtain a very good generalization of the model, holding the accuracy or targeting the accuracy of the IR camera as we have achieved so far. So now, always in the same platform, I have coupled the sensor virtual versus the real setup, imported all the measurements. What I need to do now is to calibrate AI models. So to enhance my physics-based model with some AI, that edge AI in this case, because at the end the target is the microcontroller unit implementation, remember, not the laptop. So very specific AI models that are already encapsulated in the software, and you just need to train. So basically you can open our trainer that is quite efficient, and you can train your reduced order model with the test setup that you have imported. So the good thing that you can do, the only thing that you can do in the AI model is just to choose, if we go here, which test to use in calibration, which test to use in validation, which test to use in pure testing. So here there is the list of tests, and with a very simple user interface, I have to decide which test using in training, which in validation, and ignore is the pure testing final. So let's see, for instance, test 5 new. It's a purely never seen during the calibration. Once the training is finished, we can go on a simulation and we can, for instance, test 5 new. Let's save before. And now let's run. So here you can basically see sensor by sensor This was a pure validation test, and these are basically the tests that I was showing before. So you can see the tolerance of plus minus 5 Celsius degree for each single sensor, how it is. You can also see the two polydiodes reading, and so on and so forth. So basically, in the same platform, I have integrated my model, simulate it, reduce it, calibrate it, resimulated to check if the calibration is good or not. Otherwise, I can repeat. And as a final step, now I can export it. So for instance, I have two different main formats that I usually use. One is Simulink, so a white box Simulink that is compatible with the Simulink compiler if you want to program your microcontroller through the MATLAB compilers, basically. And I can show you. So if I export this model here, for instance, the model generates automatically this Simulink block that now I can open on my MATLAB. If I go here, I just load the variables of the model. I double click on the Simulink generated. And now this Simulink has been auto-generated. You can see the full, let's say, architecture inside, as I mentioned, this white box. And now I can simulate. And you will see once Simulink has compiled how fast it is, of course, to simulate the different transients, conditions, whatever you want. So actually, you can take this box here and you can plug and play it in whatever Simulink, let's say, environment or model you have in order to basically simulate the behavior of the power module on different profiles, different VLTC class 3, 2, 1 cycles, whatever. As you can see, it's super fast. So you can even simulate hours in few, let's say, seconds. Now, the last thing that I'm going to show, and then I will finish with my presentation, is the C code. So basically, the same identical model can be exported into a firmware library with, let's say, the full report also. So basically, the model, even here, you will select, let's say, one platform, one folder, and you will build the let's say, code. And the software will stamp C code in this case. So .c.h library that you can then use in order to program your microcontroller unit. It will also give you some code generation report with memory footprint, etc., 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 number of flops, and so on and so forth. If there are any Q&A, here in the chat. So, let me start from slide 7. Is it possible to perform such real-time analysis in a thermal chamber? Slide 7. 1 second. In a thermal chamber, basically, what you can change is the ambient temperature, right? So if you place the IR camera in the thermal chamber, and yes, absolutely, you can perform the same identical test. You have just to have, let's say, the space for that. Maximize the module capacity is important, but this is only small money. But if your algorithm can detect module healthy, this is more and more valuable. Is it possible? Module healthy estimation. If for healthy estimation you mean aging, remaining useful life, degradation, absolutely yes. Because what you can do, you can implement the aging model with the same identical platform that are making use of the history of the junction temperature that we have seen so far. It is one of the, let's say, most important variables for aging degradation phenomena, and so for healthy monitoring in real time of the power module itself. So the answer is yes, and we also have our proprietary aging models that, of course, they have to be calibrated with real aging tests. So you have to perform power cycles and temperature cycles within your facility, collect the data, and using our platform to obtain an aging models in real time, which basically detect in real time the degradation of the power module. So absolutely yes. Okay. Has the model been assessed for long-term operation and temperature drift through years of usage? Absolutely yes. No, as manufacturing tolerances, you have also to take into account about aging. So you can perform the same test and collect data also with power module that they have age 0 to end of life, basically. Usually with working with supplier, 3 samples with 3 different stage of aging are enough to basically collect the data and obtain a model that is also capable of predicting well the temperature and holding the accuracy, even if it is aging. So absolutely. Is it possible to get an overview of the different scenarios presented? Which ones represents predictability of the model versus estimation? It is not clear what scenarios the calibration campaign entails. I would like to know how good the model at predicting temperatures in scenarios outside the one covered in the calibration campaign. Very nice question. The tests that I've shown in the presentation, they were all validation tests. So tests never seen during the calibration. And when I've shown the, let's say, twin fabrica procedure, you can always get the full traceability of which test has been used in calibration and which in validation. So you have always the full control of these in using twin fabrica. Okay, 1 second. What are the next steps in your project, middle, long term? Well, Newtwen has a lot of projects, actually. The same identical platform it is today used not only to generate models of power module, but for instance, electric motor, battery pack, gearbox, onboard chargers, and let's say the final scope is to obtain a sort of digital twin library and control architecture that runs inside the systems and that manage everything with high efficiency and high performance. So our mission is to bring real-time models in real time. So high fidelity models in real time. So the other application, the onboard charger I was mentioning, absolutely, DC-DC converters, batteries offshore, application not only automotive, but also industrial, energy, marine, aerospace, let's say electrified system, they are basically everywhere. So, but yeah, more than happy to arrange a separate call also to discuss this in more detail. Which time step is the model using for the TVJ? 1 millisecond. 1 millisecond is the implementation in the task of the microcontroller because the execution time is, let's say, far lower. The execution time is lower than 50 microseconds. So it's okay implementing the model in the 1 millisecond task of the micro without compromising the real-time feasibility. So the integration time step of the model, it is 1 millisecond that is equal to the implementation task in the micro in order to get the real-time behavior. Instead, the recorded time step of the IR camera, this depends by IR camera to IR camera. In this case was the cases that you have seen the presentation was a FLIR. And the sampling time was 100 milliseconds. There are better IR camera that can record much more data with even a higher frequency rate. With that, you can also see with relatively, let's say, small frequency, the swings of the temperature in the junction, also with the IR camera. Instead, the model can see the dynamic until 1 millisecond. Of course, if you have, for instance, the next generation of microcontroller unit, not a TC3, but for example, a TC4 with a parallel process unit inside, so the next generation of microcontroller, these models, they run something like 30 times faster, which makes them eligible for, let's say, smaller time step. And so for, let's say, smaller implementation task in the microcontroller, which gives you much more resolution also in the swings that are relevant basically for some applications. Okay. I think that I have covered all the questions. Very nice Q&A session. So if there are no other questions, I think that we can close the webinar of today. Hopefully the meeting was and the webinar was interesting for all of you. Please contact us if you're interested in how the software works, which is our business model, how we work together very close with customer in advanced engineering. So not only during SOP, but even during the design phase in order to optimize. And yeah, feel free to contact Newtwen team.